So, do you remember that I promised you we'll talk about the second method of writing forward kinematic? So this is going to be it, and today is an introduction to it. Hopefully we'll get to do a quick example. If it's not, it's fine, because I know whatever happens before the break, you'll forget. So I have to do it again on Monday anyway. So I have prepared a lecture for Monday that has a lot more example and review of this. So this is to give you like a quick overview of what this method is. All right. So now, can someone tell me what does forward kinematic do? It was in your exam, so you should know it. Alan, do you want to talk about it? What is forward kinematic? Yes. So in forward kinematic, given all the actuator and joints positions, which are the angles, we know where the end effector will end up, right? So we saw POE method. We use axis of rotation, two axes concept to find those out. We walked through every single joint, right? And we found what is e to the power of bracket s theta. We multiplied them and we said that it looks like that if the robot will start moving around each of those axes, and we measure where this is, we can tell at the end where this will end up, the end effector. This method is the same thing, but the good thing is that you don't have to actually develop your forward kinematic expression. It will give it to you right at the beginning. So all you have to do is hard code that in your program. But the catch is everything else, you have to figure out what they are. So the configuration of the robot, you need to write it out. In POE method, you knew the configuration of the robot. You knew all the axes, right? And you say, okay, this is 1, 0, 0, 1, 0, it's V, and then you go from there. That's the difference. So less work upfront in terms of finding the forward kinematic expression, but more of now what is the configuration of each joint, how these joints are related to each other. Your book talks about this in Appendix C, I think is one of the appendix. I think it's Appendix C. It's like a shorter chapter. So we are still trying to find the position and orientation of the end effector with respect to the effector. That did not change. Now, our approach to finding it changes. If you remember, for velocity kinematic, one of the methods we taught was the explicit method, right? Do you remember what that was? Like I'm hoping this comes on. So don't worry. Don't. Explicit. You remember? Yeah, so that is the velocity kinematic. Do you remember there was an example that I gave you, transformation matrices? And I told you if you have that, then just grab the z-axis and the position. So that's the explicit method. So DH table will give you all those transformation matrices. So the method is that, hey, this is the base frame, this is the end effector. If you have the transformation matrix of the end effector, you would grab the last column, that's the position. Grab the first 9, that's the orientation, which will find rotation from it. All right, then problem solved. That's all you have to do. Now, this method says that, you know what, we can say any robot manipulator, we can write the transformation from frame 0 to end effector if we knew the transformation between 0 to 1, 1 to 2, 2 to 3, and n minus 1 to n, which is your end effector. If we multiply all of that, we know we can do it, right? Transformation with respect to each of those. Then you have the end effector transformation. The problem is simpler now. There are assumptions that we will work through this assumption and they help us to define the configuration. We will get back to this one because right now it doesn't make sense to read off of this. In DH table, our goal is to find that configuration, right? This method says that if you can find 4 transformation in this configuration, can write 4 transformation, and you will end up finding the position and orientation of your end effect. Because we can say there will be a rotation about x-axis, all right? There will be a transformation along x-axis, there will be a transformation around z-axis, and a rotation about the z-axis. If you follow this sequence and find those information, the multiplication of that will give you the transformation between link I-1 to link I. Now, why this is specific axis? So a rotation about x, a translation about x, a rotation about z, a transformation about z. These go back to those assumptions. We only care about x and z axis. If you do that, if you multiply all of those from all, so those are all principal rotation and transformation, right? If you multiply all of those, you'll get this. We call this our big matrix. So this is the transformation from link I-1 to link I. Now, if I want to go from 0 to 1, I basically find what is theta, what is alpha I, what is di, there's one more term, and ai minus 1. If I find those 4 things, I can write transformation matrices between every joint. Now, finding those 4 things becomes your task. So this is the forward kinematic expression relationship between each frame. Now, if I wanted to find T0 per week, let's say, or end effector is on frame 3. All right, what transformation do I need to find to get there? 0, 1, 1, 2, 2, 3. If I multiply all that, I have 0 to 3, right? Pretty straightforward. I already know how they look like. I just need to find what are these 4 elements. So and they call them BH parameters. Now to find them, we need to find where is the direction of z-axis, what's the direction of x-axis, and what are those ai minus 1, bi, and theta I. Any questions so far? So I'm calling this big matrix. The big matrix. All right. Yes, and it is in, you can find it in Appendix C of textbook. Now, before we go further and talk about how do we find and what is the process of using the DH parameters, the table method, there are 2 different ways of approaching this and finding these parameters. One is the traditional method, one is the new method. I'm following the traditional, which is what your book is also using in Appendix C. This is a good reference for you to go back. Everything you'll see here, you can find online in someone's lecture or books, which you're totally welcome and fine to go and look for. And they will probably use the other method. The only difference is the frame assignment. But once your frame assignment is different, all the definitions will be different too. So what you would write will be different, but the result will be the same. Does that make sense? Because the forward kinematic has to be the same. Both robots will go to the same place, but using different methods. So if you need to know which method you're using, and you need to tell me what to do. So I know it's your own work. All right. So you're following the book, you're following this method. Some of my examples are showing the axis of the other just to show you what would be the difference. So if you saw it, you don't get confused of why they did that. All right. So we have to do 4 things. 1, we need to assign joint axes. Now, do you remember which axes the joints rotate about? The axis, right? I've been telling you, if the joint is rotating on an axis, we're gonna call it Z. The axis. It's basically coming from here. So we're gonna assign the axis of rotation to be our Z axis. the axis of translation to be our z-axis. All right, so that's number one. You will find that out because from now you will get a robot that there's no axis on it. You have to try. So far, I have given you the axis, right? So first, assign your joint axis. Once you have z-axis, can you identify x and y? You can. Right-hand rule, you find it. Now you have to actually put down x and y. Do you remember which one of these two we care about? Between x and y from what you saw for this slide before? X. So if you show z and x, I'll be fine. You don't need y, but why not just put it there, right? But x, first z, then x. Then we need to assign reference frame, which is the identifying x and y and the origin. Where is the origin of the frame? Then we are gonna find DH parameters. So there will be 4 parameters. Alpha I, AI, they look the same kind of. I don't know why they chose these 2 letters, but confusing. DI, theta I. My alpha and A look similar. So make sure you ask me which one it is if you didn't know. I try to be clear, but when I write fast, I go. Once we found those parameters, then we put them in the table. Basically, like we create a table to find all of those for all the joints, right? Then we find our T0n, which is T01, 1, 2, 2, 3, multiply all, becomes T0n. So we do this 4-step every time we're using DH parameter. I think this is an easier method. Because once you have your frames assigned, everything is just look, okay, read this and put in the table. Now, what are these parameters? What are these DH parameters? We have joint variables. You have seen them before, right? We call them theta I if they're revolute. We call them di if they're prismatic. So here's the thing. You'll see sometimes we have theta in our table, but it's not the joint variable, it's just the angle between things because we need to define the configuration. So whenever theta or d are your joint variables, we don't know their value, we just know they could vary. I put in a star next to it. This just means that this is the joint variable, the one that you ask your user to input and you change it from 0 to that value. It varies depending on the cases, right? So if you see a star, that's your variable. Now, di and theta I also describe the links connection. We will discuss this in the next slide. So it's not only joint variable, but if they're without star, they are the configuration of the robot. AI and alpha I and AI describe the link I constant and values. All right, so they depend on how your the links are connected. So you have axes and links. Axes represent where the joints are rotating about. Links are the link of the robot. So I'm gonna write it here. You'll see it again. Alpha I is the axis twist angle. AI is, this is A, the perpendicular distance between joints. So they both discuss the configuration of your robot, how the axes are angled or twisted, and how far they are from each other. If you have that information, you exactly know the configuration of your robot. So you have to provide this information to the solution. Here, a visual of the description about the link. So if this was joint I-1, and this is joint I, and the connection between them, we call it link. It doesn't always have to be a straight line, right? It could be any shape. But what we hear is the distance, which is the straight line, right? So AI minus 1 length is the mutual perpendicular between the two link axes. That's why at the beginning we have to identify the axis of rotation, the axis of the link. So you literally just draw these two because this one is rotating about this axis, this one is rotating about this axis. Now this is a 3D representation, but your pen. This one is your pen, my left hand. So these are all the different configurations that the two axes could have, right? So this distance between them, the mutual perpendicular, it's AI minus 1. Now, if they're like that, we need to see where the origin is because the distance changes as you go up and down, right? If they are like that, there's only one distance. What if they had parallel? Same distance, but they're all similar, right? So it's not unique, but this is only one unique distance, right? And it has to be perpendicular to this axis and to this axis. Thank you. Does that make sense? So, very important, if you start in sequence, finding the axis first, then AI is the mutual perpendicular between the two. AI minus 1 is the link twist, how much they are rotated with respect to each other. Again, you need to know the axes and then find their angles. All right? The other one is DI link offset. So we are not talking about joint variables yet. We're just talking about the configuration of the robot. So DI is how much the two links are offset from each other. And I'll tell you how to measure that. We have to find where the x-axes are. But they are measured in and shown with DI. So you have to pay attention that for AI minus 1 and AI alpha I minus 1, AI minus 1, D is I and theta is I. So they are lagging one subscript behind. Theta I is the joint angle. They're trying to find what's the initial angle that joint is building with the previous one. Because the rotation happens from there. So both of these tells us about the configuration of the joint. Clear? So these are the 4 parameters you need to find every time. Now, if we had a prismatic, we could have an offset plus a prismatic joint, which will be a theta plus theta squared. For DI or D star, we could also have initial angle for a joint plus some rotation that is going to happen after that initial angle. Right. Since I don't want you to work very, very hard on things that you don't have to, I'll give you 4 statements to follow to find those values. So this is an example. We are going to follow those statements every time we need to find our pH parameter. This means that finding those are basically following a rule or some statement and filling out your table, right? The most important part is to be able to identify the axis. Now here I've given you the axis because we have seen this example many, many times. We know what the end results look like. All right, so what you would do is you will create a table. This is your link I, all right? So we have 1 link, 2 link. And also, do you remember every 2 joints connects 1 link? Like there's a link between every 2 joints, so you can count your joints and then -1 is number of links. to find what I is. So I'm gonna have link 1, link 2. Then we're gonna have I minus 1, alpha I minus 1, di theta I. It's always like that. So for the first round, I'm gonna have A0, alpha 0, D1, theta 1. You don't have to write those. I'm just writing to show you the difference between the subscripts, right? I wrote, that's why my I is different. You can switch them as you want, doesn't matter. As long as this looks like an A, you put A in here. This looks, my alpha has a tail and a horn, so if it looks like that, it's up. And you'll see that sometimes I even get them confused, so feel free to tell me and ask what this is so I can fix it if it was a problem. All right, now, from these 4 statements, A0 is distance Z0, Z1 along X0. All right, now we're gonna see what that does that mean. So you have to follow this process every time you do it. Let's go back to our robot. I have shown all the axes, so I've done the first part for you. Now Z1 is pointing out the plane, right? So this is Z1. This is Z2. Agreed? Patient? Always right hand. And this is theta 1, theta 2. Now, what's the mutual distance? What's the distance between your Z0, this axis, right? Your base frame, and your Z1? What's the mutual distance, perpendicular distance between these 2 points? A1, right? That stays the same. It's perpendicular to both of them. So for some reason I said B. I'm going to change this to B so I don't have to write it again. B1. Oh, I know, because it was too many A's. It would be confusing. I changed it to B because it was a mess last time I taught this. So just calling it B so you know that is a B means distance. All right. So let's find A's alpha 0. Alpha 0 would be angle Z0, Z1 about X0. This is Z0, this is Z1, and then this is our X0, right? So if you are, so meaning that the angle has to be measured along this one. So think about rest position, right? What's the angle between these two? They are parallel. What's the angle they make with each other? 0, right? So if they are coinciding or if they are in parallel, there's no angle in between them. If it was like that, then you had an angle in between, right? Then you have to find what's X0 and you will measure the angle from the X0 axis. So right now it's 0. They're parallel, there's no angle between them. So this would be 0. DI, which is D1, is distance X0, X1 along Z1, right? So I'm going to draw this here. This is X0, right? This is X1. What's the distance between them? They coincide, right? So 0. Now, what is theta I? Now, your theta I, since this is a rotary, we know that there is some theta 1 star, right? The joint vector. We also want to check if there is any angle between them at the beginning. So theta 1, you're gonna do the second link. So I'm just putting this down so you have a process. Angle x0, x1 about z1. All right. X0, x1, right? At home position, they are on top of each other, right? Because we're just showing what theta 1 and theta 2 could be, but the home position is from theta 1 is 0, theta 2 is 0. Now, what is the angle between x0 and x1 like this about z1? Z1 is pointing out, right? The angle is 0. But if the home position was this, they had some angle, then you will see what is that about. Right now it's 0. So we have our first 4 elements. You can write T01 right now. Going back to the big matrix, putting all these angles in there, and you'll be able to find all the elements. Now, fill out the second row. So we finished relation between this. Now we're gonna write the relation between this, the other one. And this is, so there is no extra, so it will be theta 1 star. There is no extra angle between them. So it's theta 1 star plus 0 angle. This is our joint variable. So every link has to have a joint variable. This is the rotary joint, so theta 1 star. Fill this one. This is one. Sure. This is the company. This is the roller. That is just the good question. All right. The question is, why did you say A0 is B1? Why not B1 sine of theta 1? Theta is your joint variable, right? What's home position? 0, right? So theta, at the beginning, there's no theta. This is just showing how the robot would move. So your home, you always start from home position. Remember for POE, we wrote what is M, home position matrix? So same thing. So the robot actually is here right now when we write that. And then this is now the frames also move, like they're fixed on the joint, right? So they are moving together. But if you bring everything back down to home position, this is where you calculate things. Because this is a rigid body, the distances would not change as the robot moves. So we write the configuration as home position. Then we say, you know what, change theta 1 to 45, change theta 2 to 180 degrees. I want to know what would be the position of end effector. That's what we did for the homework, right? For your assignment. That's the same thing. So we always start from position. Very good question. All right. You probably found the solution was pretty simple, like the other one, right? Because the configuration of the robot is very simple. All the rotations are parallel, the same plane, right? And it's very simple robot to deal with. So I'm hoping you found B2, 0, 0, and then theta 2 star. Meaning that this is a joint variable. Now, all you have to do, go to the big matrix and plug in this value. So this is the example for when I say the big matrix, this is what I mean. This one. So there will be theta 1, alpha 0, theta 1, alpha 0, A0, D1, D1. You put those, so if you code, all you have to do is like, this is a vector, give me the matrix. And it gives you T01, T0, then you put this for T1, 2, you multiply it. So once you have this, the rest you just coded already. And it gives you the forward kinematic expression. You will get the same transformation that the last one is the position, the first 9 are the rotation elements. So if you use this method for the example that we solved, it was the same transformation at the end. Same position, same orientation. So, this, well, we don't have time to do it in class. We will do this one at the beginning of class on Monday. So I'll have you start here because a review of what happened in the class. All right. And there are some other things, smaller things I need to teach you about. Have fun, enjoy your break. I'll see you back on Monday.